Hello everyone, I'm Chenyang, and today I'll introduce our gaze interaction research, FocusFlow. More and more commercial AR/VR headsets are incorporating gaze input into their interaction design. For example, in the Apple Vision Pro, you can select an icon by gazing at it and pinching. In this interaction process, the headset detects the direction of your gaze and uses this for pointing in the 3D space. However, there is much more information in our eyes, and one often overlooked dimension is the visual depth. Now, let's imagine that we are looking out of a window. We can see the buildings through the window, and we can also look closer and closer until we see the window itself. Now you can see the doodles on the window. This example shows that we have the ability to actively adjust how far we see, and that the visual depth reveals our attention at different distances in 3D space. So now let's place a virtual window into the VR world and add information on it. When you look at an object, for example a globe, the window will not be shown. But when you change your visual depth to where the window is located, the virtual window will appear, and we can see a map on it. In this process, we change the gaze depth to select, which is natural and intuitive. So how can we achieve this interaction using gaze depth for hands-free selection? There are two challenges. The first one is how we can utilize the gaze depth signal. We can obtain the observation point from the intersection of two gaze rays from our eyes and calculate the distance from our eyes to the observation point, which is the gaze depth. However, we can mathematically see that the distance covered per degree of eye rotation increases as the observation point moves further away from us. When the observation distance exceeds 1 meter, the gaze rays of both sides are close to parallel, meaning that the eye tracker's error can greatly affect our depth calculation. Our experiment confirmed this. When the user observes at three distances of 0.5 meter, 1 meter, and 2 meter, our measured visual depth shows three distributions, and the range of the distributions increases with distance. We also tested the visual depth estimation results during the depth changing process. The blue lines become significantly more noisy and unstable as the distance increases. This suggests that we can only obtain usable visual depth at distances within 1 meter. Moreover, the presence of errors makes accurate depth estimation challenging to achieve even at close distance. Based on these characteristics, instead of using the exact value, we care more about the depth transition process. We define an activation zone, which is relatively wide. The observed target object is outside the activation zone, and the virtual window will be activated only when the user brings their visual depth into the activation zone. We also find the virtual window and the target object are placed at two different distances. Here we call it layer-based UI. The first layer is closer and the second layer is further. Users can look at the first layer or look through it to see the second layer. We can design many applications from this layer-based UI. Looking at the globe, look closer, you can see the map. Watching a video, look closer, you can have the video progress bar. Browsing a web page, look closer, you can activate a magnifier for a zoom view. Here is a demo showing how we can utilize FocusFlow in VR. By looking closer, we can select a painting on the wall and see the details. In summary, the pipeline is we first use the gaze direction for pointing and then use the gaze depth for layer selection. If we target an object and then shift our visual depth to the activation zone, the virtual window will appear. Now we have built the system, but we face another challenge. Gaze depth interaction is a new interaction method. We need to help our users learn how to take actions along the depth dimension. When we are looking at a virtual window, we can place our focus on it easily. However, when we are looking at an object, we cannot see the window, so it can be challenging for us to bring our focus closer to activate the window. So we design visual cues to help users find the window depth. It is placed at the same distance as the virtual window, so when you look at it, your visual depth will enter the activation zone and the virtual window will be activated. There are three types of visual cues. The first one is strong guidance. It is a circle in your view center, so you can reach the activation zone by simply looking at it. The second one is weak guidance. It is located at the edge of your vision, so it doesn't block your view center. Users can sense its distance through the peripheral vision and actively adjust the focus to the corresponding position. The third one is adaptive guidance. It has the same shape as strong guidance, but its visibility changes with the user's visual depth. The closer the user looks, the more opaque it becomes and therefore more visible. This design not only reduces the visual distractions, but also provides immediate feedback to the user. By observing its transparency, users can learn the state of their behavior in the system, thus better understanding and mastering depth control. Here is a video showing how these visual cues are used in the learning process. With the help of visual cues, users can easily activate the virtual window. Based on these three visual cues, we designed two learning strategies and compare their effectiveness. In the first strategy, in stage-based learning, we use strong guidance and weak guidance successively. In the second strategy, adaptive learning, we use adaptive guidance and gradually shrink its display range. Both strategies will remove the guidance in the end, which means users can only rely on their muscle memory to use FocusFlow. We designed an experiment to compare the effectiveness of the two learning processes. In this museum scene, there are three paintings on the wall, and one of them will turn red. Two groups of participants are required to learn to select the red painting using the in-stages learning strategy or the adaptive learning strategy, and we will record the time they take to activate the virtual window. The results show that the adaptive learning strategy can help more users develop muscle memory in our 18-attempt experiment. The adaptive learning strategy achieves better activation time in the learning process, while the in-stages learning shows an unstable result. As shown in the figure above, when user P8 enters the no guidance phase from weak guidance, the user has difficulty locating the target depth and fails to do so after several attempts. In the figure below, when we enter the no guidance phase from adaptive guidance, user P26 is able to locate the target depth smoothly and activate the virtual window. This shows that the adaptive learning strategy allows users to effectively memorize the target depth. So this is FocusFlow, a 3D gaze depth interaction method leveraging active visual depth manipulation. In summary, gaze depth estimation is unstable and noisy, and we design a layer-based UI and virtual window to utilize this signal. Also, three visual cues and two learning strategies are designed to help users master this new interaction method along the depth dimension. FocusFlow can be applied to various scenarios that require hands-free operation. For example, during surgery, when the surgeon's hands are occupied, FocusFlow can be a reliable way to select information. More applications can include Launchpad, Quick Preview, and some accessibility features. For future work, we need to improve the adaptability of virtual window under different scenarios, such as moving and changing depth. In this work, we use the gaze depth as a binary selection. However, it also has the potential to be a continuous input if the distance is close enough, so more interaction techniques can be developed. In addition, we are curious about what happens in the learning process, how adaptive learning can be improved, and what is the mental model for learning. Lastly, other inputs like gestures can be merged with FocusFlow, and more applications can be designed. Some quick takeaways. Gaze depth interaction is efficient and accurate for hands-free selection, and more applications can be designed using this layer-based UI. The active visual depth control can be learned and become a muscle memory through short-term learning. The adaptive visual cue is effective in providing feedback, which is important for users to understand the system. This is FocusFlow. Thank you for listening and welcome to read our paper.